Okay, good. I've pressed start recording this time, and it looks like my picture's showing up in the little bottom corner right there. And we've got the ever so thrilling first slide frame for our PowerPoint presentation today, where we're going to be talking about the mechanical properties of materials. Now, last week we talked about a broader range of chemical properties, heat of fusion, um, uh, fuel properties, insulative properties, conductive properties. Today we're going to focus down a little bit on a lot of the things that really matter to us, specifically in regards to strength and structure when we're building things. Before we jump right into the PowerPoint, though, usually I begin this lesson by having a class discussion about what is the strongest material. And it's interesting the answers that you get. You get many of the very common ones, where people will talk about titanium and carbon fiber and various versions of hardened steel. And every now and then there's something that comes from just a little outside. And one of my favorites was a student suggested water was the strongest material. And his explanation was that you look at the world around you and it's all been shaped by water. It doesn't matter how big or how strong a mountain is, water will eventually crack it and wear it away. And it was a really interesting take on a question that I put out there because really there is no answer to what is the strongest material. There's all sorts of different applications where a material might be strong for that material or useful in that application. But to say that there's one strongest material is like saying there's one type of strength. And so, anyways, I've got this little PowerPoint that's available for download or spreadsheet that's available on download from D2L that goes through and talks about some of the materials that are available nowadays. And since I've made this up, some of those materials have been shifting from what I've called research stage right in here and moving into actual applications. So graphene at the time that I made this document several years ago was really there were no commercial applications of it. And now I've actually seen bicycle tires advertise that they've got graphene embedded in them. I don't think it does anything useful for them, but it uses the latest buzzword. And, of course, you could embed a two-dimensional sheet of carbon atoms into rubber bicycle tires to make them, I don't know, more flexible so they have lower rolling resistance or better traction or better wear life or whatever you're looking for. Usually lower weight is what they're going for in the cycling world. But anyway, so yes, graphene showing up. But the problem we run into with graphene, of course, is its fatal weakness. It's only one atom thick, and we haven't figured out how to make anything bigger out of it. But it could take carbon fiber to another whole level if we're able to make bigger sheets of graphene and find a way to bond them all together. We have seen some carbon nanotubes being used in a few applications, certainly not as a rope. And I think we're still somewhere in this fatal weakness that our longest piece is still somewhere only 20 millimeters long. And spider silk, and at this time of year around Vancouver, we're all familiar with spider silk. When you think about the strength and of those tiny little pieces to hold a spider, sitting in between two objects far apart, or how annoying they are to try and pull off your face when you walk down the stairs and there's spider webs all across the stairs. Spider silk is just an amazing material that is produced in nature and we haven't really figured out how to replicate it for human applications yet. There's been a few things done, like I say here, they figured out how to make hamsters have spider silk proteins in their milk, but they just don't come out as good as the real thing. Now, we've got our high tech and expensive materials, and these are ones that you'll quite often see, you'll be able to buy carbon fiber things. It's pretty common. In fact, we've laminated things up with carbon fiber here in the shop. You need to know what you're doing before you do too much work with carbon fiber because It's a high performance material, and if you use it incorrectly, then you don't get the high performance characteristics of it. You just get the flaw characteristics of it. But carbon fiber has done some amazing things. The Boeing 787 jetliner achieves something like 20% fuel savings versus a similar aluminum plane because it's basically made out of carbon fiber and Kevlar composites. There, what else do we have in here? We talked a little bit about spectra ropes in some of our plastics presentations, and down here we've got a metal that was used in the original iPods and some of the original iPads. And if you'll remember, if you think back to some of the original iPods, they had a very distinctive, shiny, smooth, hard metal finish. On the back of the case, not so much the front that was glass. And this was a really cool casting resin called liquid metal. And I don't know where it's gone. We haven't seen a lot of it lately. I guess it's been replaced by more advanced machining of aluminum because we tend to see a lot more aluminum cases in phones and that nowadays. But it was a very cool casting alloy. And by cooling it super, super duper quickly, they were able to make it very strong, very hard, and very shiny. So it was quite cool. And of course, carbon fiber composite, which is different from pure carbon fiber because to actually make anything useful with carbon fiber, what you have to do is you have to embed it in epoxy to form it into a composite structure where all the fibers are held together by an epoxy matrix. So there's hard materials on here, and diamonds are officially still the hardest material, but people have been doing some experiments and they've managed to come up with tiny little trace parts of these things called diamond nanorods that actually will scratch diamonds. So they're like, man, that's a little bit harder than diamond. And of course, things we see in the shop are tungsten carbide and silicon carbide that we'll tend to use on cutting bits, so quite a bit harder than the materials that they're going to be cutting. And although there's all of these super fancy materials, the common materials that we might work with in the shop are also really amazing structural materials. And when you learn how to use them properly, knowing how to use something like wood properly allows you to build very strong, rigid structures. And if you know how to use wood properly, you're probably going to make a better wood structure than carbon fiber structure if you don't know how to use the carbon fiber properly. Because the more advanced material you get, the more challenging it is to access the benefits of those advanced properties. So, for instance, there's some really neat materials in here. And when we look at the properties that I've been talking about for the materials, we're going to talk more about what these mean in our PowerPoint that follows here in just a minute. But we've got the yield strength, okay? And the yield strength is measured in megapascals. We'll talk all about that. But basically, a higher number here is better, and an ultimate tensile strength. So we've got two different strength figures right in there. And what we're looking at is the yield strength or yield stress is how much force over a cross-sectional area you have to apply to a material in order to make it stretch and stay stretched. So when something has plastic deformation, that's because you've exceeded the yield strength. So right in here, I've exceeded the yield strength, but it hasn't broken yet. So I haven't quite exceeded the ultimate tensile strength. So your yield strength and your ultimate tensile strength are often related, but in order to get to the ultimate tensile strength, you have to exceed the yield strength. There's also this form value called E, also known as Young's modulus or the elastic modulus. And again, we'll talk more about it and why it's measured in gigapascals, which are very similar to megapascals. They're just 1,000 times bigger. And that relates how much the material shifts while it's in its elastic range. So We'll come back and we'll define that term a little bit later on. Strain to failure is one that actually makes sense and is measured in percentage, a unit that most of us get. So how far can you stretch that thing before it fails? So a really ductile material is one that can stretch a long way and absorb a lot of energy before it fails. The density is important because all of these measurements down here are done based on cross-sectional area. Well, if you're trying to build something light and get a good strength to weight ratio, sometimes you can use more of a low density material rather than using a little bit of a high density material. So you need to account for the weight of the material, the density as well. So critical material property there. And when we take a look at the ratio of the strength to the weight, then we come up with a strength to weight ratio that gives you an idea of how strong a given mass of this material is relative to another given mass of a different material. So for instance, if you've got a kilogram of fiberglass to work with, and we use S-glass, the high strength fibers, okay, you're going to get somewhere around 1899 is your value for strength. Now that's a dimensionless number. It's just a ratio that we're looking at here. But bamboo, for the same amount of weight, is only going to give you about 1/3 the strength. And when you come down in here, wood is doing okay. What's really interesting is when you come to the strength to weight ratio for good wood, okay, somewhere around 0.63 density. That low density gives you approximately the same strength to weight ratio for good hard wood as for basic aluminum alloys. Yes, we can make stronger aluminum alloys, and yes, we can make stronger steels, but if you look at this, they're all in about that same range right there. So if you can make something out of aluminum, you can probably redesign it and make it out of wood and have it come in at a very similar weight. There's a lot that goes on in the structures course that we'll do next semester that sort of addresses that, because that's a very broad statement and not always 100% true. There are also other material properties that go into your materials choice, and sometimes wood is the correct material, sometimes steel, and sometimes aluminum. But if you just look at strength to weight, it's amazing how good wood is relative to especially something like plain carbon steel. And you see that pop up from time to time. Maybe not so much with modern planes because we've got more advanced metalworking resources now and more advanced metal machining and fastening and welding, and we can make metal parts really, really reliably. But if you think about things like the Spruce Goose and pretty much any high performance airplane built prior to World War II, those were all made with significant amounts of wood in them, including many of the famous planes that you know from World War II. The Mosquito bomber, the fastest plane for much of World War II, was produced almost entirely out of plywood, because wood has a very good strength to weight ratio relative to aluminum. And when aluminum's in short supply and you've got lots of cabinet makers who know how to work with plywood, you make your fighter bombers out of the material that makes good fighter bombers. So anyway, there we go. We've got some strength to weight ratios, and as I say, this all comes about through a discussion of what is the strongest material, and Daryl gets his name forever embedded into this document for his suggestion of water many years ago, because it was. I love it when people think outside the box and have relevant comments and insight and a reason for their choices. So you'll find that document there, and we'll talk about what some of these properties mean as we go through with the PowerPoint presentation. So here we go. I know you've been looking forward to this. You got your coffee ready, right? Okay, I clicked. There we go. We're going to be talking about mechanical properties. And this describes how the materials behave when interacting with other materials. So, when I take my aluminum pop can and I squeeze it, it's interacting with my fingers. Okay, why does the pop can squish but my fingers don't? And although sometimes there's tie-ins and the reasons why our mechanical properties are a certain way, it's important to remember that right now we're just looking at mechanical properties, but there's chemical properties, electrical properties, thermal, optical, all sorts of other properties that will play a role in material selection. So not everything revolves around mechanical properties, but in almost any engineering or design application, you have to consider these mechanical properties as you design. And the key mechanical properties that we're going to be looking at are the yield stress, the ultimate tensile stress, hardness, which really comes down to the yield stress right at the very surface of the material. Hardness and yield stress are often quite closely related. The elastic modulus, how far something stretches when you pull on it. Strain to failure, how far something will stretch when you pull on it. Toughness, how much energy something will absorb before it breaks. So we've had brittle things that absorb very little energy and break easily, and very tough things that absorb a lot of energy and are really, really hard to destroy. And then a little bit we'll talk about fatigue resistance. How many bend cycles can a material resist? Because that's also important, particularly in rotating equipment or something that's going to be subject to multiple high stress loads. So before we get into talking about any of these properties in detail, we do need to touch on a metric unit that may or may not be familiar to a lot of people. So if you're familiar with the Newton, then please go ahead and skip on to the next slide. But the Newton is the metric unit of force. Okay, now it's used you can use it to express the weight of something. So for instance, if I have a 1 kilogram mass, the force of gravity acting on it is approximately 10 newtons. Okay, so Newton is a pushing force. Sometimes it results from the interaction of gravity and mass. Other times it comes about because I am pushing on my pop can with a force of, I don't know, 5 newtons, and the force I'm pushing on the pop can in this direction is greater than the force of gravity acting in this direction. So the net units of force are lifting it up, and this will start to begin to accelerate upwards. So there's this little glitch for people who've not had a chance to pause and consider this, because we're used to getting on a scale and saying I weigh so many pounds. Oh, imperial units. Loathe imperial units. I just happen to use them. We get on a scale and it'll tell us we weigh so many kilograms. And that's not quite true. What the scale's actually doing, it's measuring how hard you're pushing down on the scale. The reason that you're pushing down hard on the scale is because your body has a certain mass. That mass interacts with Earth's gravitational field, and Earth's gravitational field pulls on an object. When you're near the surface of the Earth, which is where hopefully we are spending most of our time, it pulls on an object with a force of 9.8 newtons per kilogram. Okay, now for all of our intents and purposes in here for doing all your math, 9.8 is a really nice number to round off to 10. So long as you remember that it's really 9.8 in any of your calculations, feel free to use 10, because it's sure a lot easier to multiply a number by 10 than it is to multiply by 9.8. Also, by increasing it a little bit, we tend to add a small but non-zero margin of error, so we're making our error in the right direction for most applications. So yeah, now this would compare to, say, standing on a scale on the moon. Your body on the moon would have the same mass that it does here on Earth. but the moon's gravitational field is weaker. So you would, if you stood on the scale, see less gravitational force pulling you down. Now, a proper scale would report your weight on Earth in newtons and on the moon on newtons, and then that would read correctly and it would make sense. But on the moon, it would tell you that your body had less mass, which is not true. Your body has the same mass on the Earth as on the moon, but due to the weaker gravitational field on the moon, your body would have about 1/6 of the gravitational attraction to the planet's surface. So there would be 1/6 the number of newtons pulling you down, which is why, if you look at old videos of people walking or trying to run on the moon's surface, you can't really run in the same way. They also ran into problems with getting traction for the moon rovers because there wasn't enough gravitational force pulling the moon rover down. So when they started up their wheels, the wheels would start spinning, because in order for the wheel to have interaction with the surface, you need that gravitational force pulling it down. And yeah, no, putting the arrow fins on your car on the moon doesn't help that much either. Anyway, so the Newton. Basically, if you want a feeling for what 1 Newton of force is, while in Earth's gravitational field and close to the surface of the Earth, take a 100-gram weight, put it in your hand, and you will feel 1 Newton of force pushing downwards. So that's the Newton. Now, the Newton comes in really important when we talk about stress, okay? And we're going to be talking about stress a lot. Not the stress that you're under right now that causes you to want to have, how do I refer to it? A highly concentrated ethanol, highly concentrated aqueous ethanol solution on Friday afternoon. No, not that type of stress. This is the type of stress that is occurring within the material in the sense of yield stress and ultimate tensile stress. And so the stress is mathematically defined as the force acting on the object. Okay, so if we've got a piece of aluminum like so, okay, and I'm pulling on it like this, the force that I'm pulling with is the force that we're talking about. And the area that we're talking about is the cross-sectional area. Zoom in right there. The cross-sectional area of the pen right there. So if I pull on it like that, obviously it would be less stressed if it was a bigger piece of aluminum and I was grabbing a large diameter piece of aluminum because I'm still pulling with the same force, but I've got a bigger cross-sectional area. If I move up, here's something a little bit bigger. I pull on that, there's more material to distribute that force, and therefore I've got less stress. So let's take a look at the units that we're using in there. So our force will be measured in newtons. Our area will be measured in we take a look at the cross section. Basically, you take your sample and you chop it in half. And then what we'll do is we'll do a little bit of math and figure out what our area is, our cross-sectional area in square millimeters. And then our stress will come out in megapascals. And that's because the base unit, so keep in mind metric will have a base unit and then a prefix at the beginning. So a megapascal is actually 1 million pascals. So our base unit of the pascal is 1 Newton per square meter. So a square meter is a pretty big cross-sectional area. So if you had 1 million newtons acting on 1 square meter, that would be the same as having 1 Newton act on 1 square millimeter. Okay, so we tend to use the megapascal right here, but it all derives back from that Pascal unit of 1 Newton per square meter. You'll also see the Pascal used as a unit of pressure as well as a unit of stress because it's very similar. It's force over an area. So our standard atmospheric pressure at sea level, sometimes you'll hear it referred to as 15 pounds per square inch. If you hear somebody who uses those obsolete, awful imperial units talking about it, but the correct way to refer to it in metric nomenclature is the standard atmospheric pressure is 101.3 kilopascals. So you can work that through in your head and say that's about 1/10 of a megapascal. So for every millimeter square on the surface of your hand, there is a tenth of a Newton force acting on it, which is not insignificant when you think about it. Okay, tenth of a Newton, we said a Newton is roughly the same as what you'd feel holding a weight of 100 grams. So that's roughly the same as the weight you'd feel holding 10 grams, acting on 1 square millimeter of your skin. Well, you've got a lot of square millimeters of skin here. Air pressure is really compressing us and holding us all together. Well, our skin is doing most of that work. But anyway, air pressure is pushing down on us all the time. And thank goodness for that, our blood would all boil and disappear. So yes, the amazing thing is I had that slide referring to those wacky Americans, and that was like more than 4 years ago that I put that in there. So I had no idea just how many levels of wacky that nation could take it to, but all said, could be worse neighbors to have. I can think of a lot of countries with 300 million or more people that I wouldn't be quite so happy to share a border with. So anyway, there we go. Don't worry about their units, but you might in some of your documents see them refer to something as a KSI or a PSI. And a KSI is just 1000 PSI. They tried to get in on that whole metric prefix thing, but they did it wrong. Anyway, let's use this and do a calculation. Okay, so you go down to the shop and you get a piece of metal, and it's 4 millimeters thick, 25 millimeters wide. In other words, about 1/8 of an inch thick and an inch wide. I'm weak. I fall back into imperial sometimes. A piece of metal 4 millimeters thick by 25 millimeters wide is pulled with a force of 5,000 newtons or 5 kilonewtons. Okay, so let's get a sense first of all. 5,000 newtons, what's that going to be like? So there's 10 newtons to a kilogram. So that's like hanging a 500 kilogram weight off of it. Okay, so basically, I don't know what, 5 big guys hanging off the end of that. So we know the formula is going to be force over area. And we know that the force is going to be 5,000 newtons. We need to get the area. And I suspect math class has been doing a lot of area calculations with you. And we do actually touch base and swap notes back and forth, and sometimes try to make sure that you're seeing the same things in different places. The cross-sectional area, of course, 4 millimeters by 25 millimeters is going to give you 100 square millimeters. So the stress is not so hard to calculate. We'll even use some little engineering nomenclature there. S equals F over A equals 5,000 newtons over 100 millimeters squared. Really important to keep your units in here when you're doing the calculation so you can actually remember what you're doing and take a look back at it later on, so see if it makes sense. And that's going to come out at 50 megapascals. Okay, we could do the same thing for a round cross section. And so wires tend to be round, 900 kilograms. See, I've changed the way that question's phrased. Last time I gave you the force in newtons. This time I say it supports a mass of 900 kilograms. Okay, what's the stress in the wire? So in this one, you need to say, okay, what's the force in the wire? So if it's supporting a mass of 900 kilograms in Earth's gravitational field, that's 10 newtons per kilogram, even though it's really 9.8, but we don't worry about that. So that's 10 newtons per kilogram. So 900 times 10 gives us our 9,000 newtons of force acting within that wire. Now we calculate the cross-sectional area. And one of the things that you do have to watch for, and I'll mess around with questions like this on a test, is sometimes I'll give you a radius and sometimes I'll give you a diameter. And as you know, the area formula is pi r squared. So don't mistakenly do a pi d squared. That just doesn't work out. It comes out 4 times larger than it needs to be. So area equals pi r squared. There we go, 78.5 square millimeters. So in this case, our stress is going to be 114.6 megapascals. So a little note down here at the bottom, just as I've worked through this equation right here, showing you step by step how to do it, keeping the units in place, make sure that if you're doing a test for me, that you do it that way as well. I will be looking at it, and keep in mind that also you need to be able to do it step by step, because in the not so distant future, it's going to be your job to explain how this sort of thing works too. So make sure that you know how to explain it. The other thing that happens is that this lets me know whether you use the pi button on your calculator or whether you use 3.14. And after you've done a number of calculations, your answer could be different from my answer if I use the pi button and you use 3.14, and then we multiplied it by a large number and then did 2 or 3 more equations later on. If I can go back in your answer and find out, oh, yeah, that's why we're off by a small fraction, then I'll know what happened. Okay, so that's stress. Stress causes strain. The more stress you have, the more strain results. Strain is the change of length in a material. So when you pull on a material, it's going to get longer. When you push on a material, it's going to get shorter. And every material does that, even though sometimes it's not immediately noticeable. When you stand on the floor, your foot not only compresses the sole of your shoe, but it compresses the floor down ever so slightly, just a tiny little bit of amount, because you're putting stress on the floor. You're applying mass to the floor, and the floor is staying put. So obviously, it's got to be absorbing that force, and it's not moving. Well, there is just a little bit of movement. And we can experience that on like a sprung dance floor. I don't know how many people have had a chance to go down and dance at the Commodore Ballroom. Really something kind of cool. It's really built to be springy down there. But gymnasium floors are built out of wood, and it's called a sprung wood floor for just that reason, so that they can absorb a little more impact, and they'll deform more than a hard concrete floor. But make no mistake about it, even that hard concrete floor, when you stand on it, deforms a tiny, tiny, minuscule little amount every time. All right, so stress causes strain. Strain is the change in length that a material experiences when loaded. Maybe change in shape is a better word. And the symbol is a small e. And so it's a comparison of two measurements, the initial length and the final length. And the formula is, well, it looks fancy, okay, but there's nothing really to it. The strain is just the final length minus the initial length. So you do that first, it's in brackets, and then you divide it by the initial length. It's basically a percentage calculation. That's all you're doing. So, so it's the change in length. Delta L would be another way to say that, divided by the initial length. Let's do a calculation. Should be pretty obvious. Yes, there we go, Tarzan. Tarzan swinging from a vine. Vine was initially 10 meters long, but with Tarzan's weight added, it stretches to 10.5 meters long. What is the strain in the vine? Okay, so here we go. We've got an initial length. We've got a final length. We subtract the initial from the final. So with Tarzan hanging off that vine, the vine became 0.05 meters longer, so 5 centimeters longer. Hold on just a minute. Oh, right. Sorry, 0.05. It's 5%. Getting ahead of myself here. Hope y'all caught that. Okay, so 10.5. That's really a long length. That must be one stretchy vine. Length final was 10.5. Length initial was 10. The result of that calculation was 0.5 meters longer. Okay, and then we divided by the initial length of 10 meters, and this gives us this formula right down here. So our strain, E, equals 10.5 minus 10 divided by 10, or 0.05, and then we turn that into a percentage by moving 2 decimal places over, and we say the vine experiences a strain of 5%. Okay, and I haven't clicked on that link in ages. I'm curious where it goes. Oh, looks like somebody did some research. Could a human swing on vines through a jungle? I suspect the answer is no, but click on the link to find out. So we've talked about stress, strain, and Young's modulus. Okay, the stretch that the strain that happens in there, and so now we've got plastic and elastic deformation. So these are two types or two ways that a material will change shape. And plastic deformation is something that you see, well, in a lot of plastics. You pull on them, and that little bit that you see where they get longer and they just keep stretching and stretching and stretching in there, okay, is plastic deformation. Now you can see that there's a little bit of elastic deformation in there too. So when I pull on that, some of the damage that I've done remains in the material. The plastic deformation is what remains after you remove the load. Okay, the elastic deformation is what springs back. So if you pull on a material and you don't permanently change its shape, then that's elastic deformation. So when you step on the floor tile and the cement underneath it, or the wood in the gym, that always springs back. And so long as that always springs back, then you've caused elastic deformation. Okay, it returns to its original shape. But if you happen to drive some exceptionally heavy thing over the gym floor, you might cause some plastic deformation. Well, not so much in a wooden floor. Wood doesn't really deform plastically that well. It's either elastic deformation or something starts to crack. But certainly in a softer material, if you drive a heavy vehicle over your lawn, you're going to get some plastic deformation as the lawn moves out of the way of that wheel. So if something does not return to its original shape, then it's been plastic deformation. In other words, it stays bent. So elastic springs back, plastic stays bent. And the barrier between elastic and plastic is the yield stress. Okay, so this is the stress, the amount of force inside a given cross-sectional area of that material where it transitions from elastic to plastic deformation, stretches and stays stretched. And this is generally, in most projects, what we'd consider the failure point for the material. Because what tends to happen is once you've exceeded the yield stress, you tend to keep exceeding that yield stress, and the thing will get longer and longer. As it gets longer and longer, the material will get narrower and narrower, so the stress actually goes up. So generally, once you've exceeded the yield stress, you're well on your way to exceeding your ultimate tensile stress. And there are some materials that will work harden. As you stretch them, they'll get stronger and they'll rise to the challenge. But basically, if something exceeds the yield stress, we say it's broke. And so here's some examples of materials with different yield stresses. And you can see that the composites like aramid have quite high strengths. Okay. And then down at the bottom, we've got things like just plain old high density polyethylene. Now, keep in mind, those also have different densities. So if we were to do a strength to weight ratio, it wouldn't be nearly as much of a wipeout as you see on the board right here. Now, yield stress is relevant for every material, but in brittle materials, where as soon as you get them stretched to the point where you're at a point of no return, and they have no plastic deformation to speak of, so they will have their ultimate tensile stress be the same as their yield stress. And you can say ultimate tensile strength and yield strength. So long as word starts with an S, I'm okay with it. Okay, so ultimate tensile stress, the material at which something breaks. And in most of our alloys, because we don't tend to work with really brittle metals, we're going to see the UTS be a higher value than the yield stress. Because as you start to bend a piece of metal, it will work harden and it will absorb energy and it will resist you more and more as it hardens in there. On the other hand, that starts to cut into your fatigue resistance. So we'll take a little bit look at that. But basically, we tend to talk about this in the context of a tensile stress, because when you start pushing on things and start dealing with compressive forces, then all of a sudden the length of the material that you're compressing starts to become an issue. So we end up getting buckling. So a long, narrow column is going to buckle differently than a short, fat one, even though the material and its UTS is the same. But when you pull on something, it always behaves the same way because buckling's not an issue. Okay, if you've got weird strain rates on there, it doesn't always behave the same way sometimes. If you think about silly putty, you pull it fast and it snaps. But basically, most of the time, tensile is much easier to consider than compressive strength. And finally, we've got, I say finally, we've got strain to, there's more coming. We've got strain to failure right here. And this is how far a material will stretch before reaching that ultimate tensile strength. So as we pull on a material, we have elastic deformation. That's the deformation that springs back until we hit the yield stress. And then we enter the range of plastic deformation, where it stretches and stays stretched, or bends and stays bent, and then how far we can pull it from the start to the end before it finally falls apart is what we call our strain to failure. And we just use the same calculation, the strain calculation. And some materials are really amazing with their strain to failure. That darn spider silk, you pull on it, and it just it's really hard to break that stuff. It's so tough. Generally, a high strain to failure is also associated with a high degree of toughness. In other words, it's not brittle. So one more in here that relates stress and strain together is the elastic modulus, or Young's modulus. And this will tell you how much a material stretches while still in the elastic range. So before this is only valid up until the yield stress. After that, you're in the plastic range and all bets are off on using nice formulas to describe how it behaves. But our stress is causing our strain. Well, this is just the ratio between the two of them, and it's going to predict how much a material will deform. And so high elastic modulus, or high modulus materials, are going to deform less for the same amount of force than a lower modulus material. All right, let's do a calculation on this. So we've got some aluminum cable, and I'm assuming solid aluminum cable because yes, we can go in and we can do, how many wires are in that aluminum cable? There's one, and it's solid. Makes the question easier. Let's do it this way. So a 6 millimeter diameter aluminum cable, 3 meters long, supports a weight of 400 kilograms. How far does it stretch? Everything stretches, everything bends, everything breaks. Let's calculate how far. So calculate the load is step number one. Okay, 10 newtons per kilogram, even though we know it's really 9.8. So 400 kilograms times 10 is 4,000 newtons. Okay, so there's 4,000 newtons of force acting in that wire, in that cable. Then we're going to calculate the cross-sectional area. Remember, you've got to base it on the radius, which is why I'm using 3 millimeters here, because it says it's a 6 millimeter diameter cable. Gives us 28.26 square millimeters. And now we can calculate the stress. We have 4,000 newtons over 28.26 square millimeters is 141.5 megapascals, 141.5 of those little newtons for every square millimeter. Now, This is where we have to start looking up some values to figure out how things behave, because you would go to your chart of materials, either what's the strongest material or one of the tables that I've given you in this presentation, or go online. Nowadays, you can actually pick up your phone and just say, okay, Google, what's the yield stress for aluminum? And it'll probably give you a pretty good value. There are some significantly different yield stresses in aluminum at different alloys, so it might ask you to specify an alloy. But in here, look up the elastic modulus, and that's pretty much the same for all aluminums, regardless of alloy. Convert it from gigapascals to megapascals, okay? So just keep in mind, going from giga to mega, it's a difference of 1,000. So 69 gigapascals, 69,000 megapascals are the same thing. And take your 69,000 megapascals, and that is going to be, when you punch it into this formula, you're going to say 69,000 megapascals equals 141.5 divided by strain, because your stress, in this case your yield stress, is equal to, well, we've got the force over the area, and then your blah, blah, blah. Your, your strain is equal to your force multiplied by your words. Words, come to me. Your strain is equal. Let's go back one slide. There we go. E. Your elastic modulus is equal to your stress divided by your strain. Right in there. Come back over here. Okay, here we've got our stress on the top, our strain on the bottom, our elastic modulus for aluminum that we looked up at 69,000 megapascals. And so then we can do a little bit of calculation, and we can say that our strain on the material is 0.002, or that's 0.2%. And here's part 2 of that calculation. So we know the cable's 3 meters long. So now we can take our strain, we can punch it into our formula for strain, and we put our initial length in there, and we discover that our elastic cable stretches 0.006 meters, which, if you bump that around, is 6 millimeters across its 3-meter length. Not very much, but it does stretch. Whew, you got the full lecture experience of me losing track of what exactly I was calculating while I was talking there. But anyway, the formulas are all right there in the PowerPoint, and you can go through and you can double check it all out. Now, you do have to double check when you're doing some of these calculations to make sure that you stay within the elastic range. So the elastic range is from 0 stress up to your yield stress. And for aluminum, we look it up, and if you go over 400 megapascals, you're no longer in the elastic range. You've shifted into the plastic range. Now you're actually permanently damaging or bending the material and breaking it. And so anyway, these calculations only apply in the elastic range, and that's why Young's modulus is also known as the elastic modulus. Okay, so when we start putting some of these together, we end up talking about things like toughness, ductility, and brittleness, and basically they all get around the same idea that when you hit a material, you want it to absorb impact energy. You don't just want it to shatter. So if you think of glass, okay, when you whack a piece of glass, it's pretty easy to cause all sorts of breaking in there, because glass has no ability to absorb the impact energy. But if you look at a nice tough piece of steel, then that steel can definitely absorb that impact, because steel has some toughness to it. And so what you're looking at in terms of your fracture energy, and what differentiates a tough material from a brittle material, is the amount of work you have to do to make it break. And to make that happen, there's a combination of yield stress, ultimate tensile stress, and the strain to failure, how far you can pull it. And all sorts of different factors come into play. And some of these factors we know about now, but we didn't know about 100 or more years ago. And certainly we pay more attention to them now than we did 100 or so years ago, because there's been some research done on recovered bits of the Titanic's hull that discovered slightly high concentrations of sulfur in the steel that was used to make the Titanic's hull. And while that doesn't necessarily affect the toughness of steel at room temperature, what it does is it affects the temperature at which steel starts to get brittle. So on that night out in the North Atlantic, when the Titanic plowed into an iceberg, it was quite chilly. And it's possible that some of that steel was not as tough as it should have been at those temperatures because of this slightly increased presence of sulfur in the steel. Now, it's not to say the Titanic wouldn't have sunk. Icebergs are big and they're a problem, okay? And the Titanic nailed that one like nobody's nailed an iceberg before. But it might not have ruptured so many of the waterproof compartments so that they weren't able to get all the survivors off the ship. And so they could have had there were rescue craft on their way. And if they could have just kept one or two more chambers of the Titanic intact instead of having them crack, then the Titanic might just be another boat that we never really heard of. Okay, so anyways, some of these little things actually have really big roles to play in determining how people live and how people die. Anyway, the toughness of material, basically you take a big whopping hammer, you lift it up in the air, and it swings through and it hits it, and the height of the hammer comes out the other side, determines how much energy is left in the hammer swing, and you take how much energy the hammer started with, subtract how much comes out the other side, and that tells you how much energy was absorbed by the piece that you nailed with the hammer. Now, the way we tend to see this is on a stress strain curve. And so we've been using some of these terms for a little bit. And let me just see right here. I've got a pen and I can take my pen right here and I can doodle on here now. So let's see, right in here we've got our elastic region. Okay, now our elastic region is really important because that is what we see up until the yield stress. So everything in green right in here is our elastic region of a stress strain chart. When what this chart is showing us is that when we start pulling on an object, so we'll get a big giant machine that will just start putting massive amounts of force onto a piece of material. And as we pull on it, that piece of material will start to stretch and it'll get longer, okay? Now, if it's following this nice straight line, okay, as we keep stretching it, as the stress keeps going up, and it does it in a linear fashion, and it takes twice as much stress to cause twice as much strain, then we're still within the elastic region usually. And if I release that force or let it go back to its normal shape, it will usually slide right back down this line right here and come back to our starting point where there's no stress and there's no strain. But once we get past that yield point right in here, now it's starting to bend and stay bent, or stretch and stay stretched. So it's coming along right in here. And in this region, if I stop pulling on it, it will still come back, but it will still be a little bit stretched, even though it's no longer been under stress. That strain is going to remain permanent. And if I stop right here, just before the failure point, that's going to come right back along that elastic line, and I'll still have strain remaining in that material. Now, as we start to go through right here, the material gets thinner and thinner, but the same thing, what starts to happen in a lot of materials is they'll undergo a process called work hardening, where we'll talk a little bit later about how that works, but basically the failures inside the material will start to pile up on each other and they start to form roadblocks to other failures, so that you makes it harder to stretch it. So you see a change in the stress strain curve. By looking at the stress strain curve, what you can see is that we've got hard and brittle materials. And our hard and brittle materials, excuse me, our hard and brittle materials have a very tiny area under that stress strain curve. Oh, well, that I should know better than to use a mouse, obviously. Click the wrong button there. And so we fill that in right there. But if you look at the area under a hard and strong, you can see that this area is much larger. And here we've got a hard and tough material that's also got a fairly big area under the curve, or even a soft and tough material. They all have more area under that curve than the hard and brittle material did. So let's see, erase all ink on slide. That looked really ugly. Alrighty, basically toughness is a very important factor, particularly when you think about anything that your students might be designing. We have had a couple of cases. I used to build electrothon race cars with my students, and the students would sit on them and drive them, and they were getting up to the point where they were, in some cases, going 60 kilometers an hour. And it was really difficult to know if they'd done proper welding and if they'd got a tough weld or a brittle weld. And there was a couple of places, it wasn't my students who demonstrated this, but one of them was going down the back straight at the old IndyCar track, and their wheel hit a bump, and that bump, this was as fast as they'd been going. There was just a little rock or something, but when they hit that bump, that sent a shock into their steering system, and a student had welded up the steering system. They'd used a high alloy bolt and hadn't properly heat treated it. This had resulted in a brittle connection, very, very strong connection, but very brittle. And so that just went snap and it shattered, and the wheel came off, and they did a roll, and thankfully they had a roll cage and all their safety gear on. But that was about the point where we started to say, oh, kids could hurt themselves doing this. Like, hurt themselves bad enough that we'd have to go to court to explain what was going on. And since we didn't like the idea of paperwork, we decided not to pursue that too much further. I mean, since we don't like the idea of kids getting hurt, we decided not to pursue that too much further. Anyway, good idea to have a ductile material, one that can handle a fair bit of strain. It's tough because you'll see it start to fail, and had that axle being made out of a ductile material, it still might have failed when it hit that bump, but it would have failed plastically, and the wheel would have bent a little bit, and they would have made it into the pit, and we would have been able to see that damage and know what was going on instead of having it just shatter out on the track. And speaking of shattering, hardness is another material property, and as I was saying earlier, it's largely a measurement of the local yield stress at the surface of the material. And we'll use hardness a lot as a proxy for yield stress when we're doing some of our steel hardening later this year. And we'll use something called a Rockwell C hardness machine. And what it does is it takes a diamond braille, no, not the Star of India, but a tiny little industrial diamond, and then you put a given amount of force called the preload on it, and it just puts it down beneath any surface imperfections. Then you allow a big load to go on it, and it pushes it down right there. And then you relieve that load, and a micrometer tells you how far down it is in that material now. And so that amount of plastic deformation in there is going to be an indication of the yield stress in the local range at the surface of the material. Hardness is often associated with brittle materials because you tend to get a super high yield stress, but you don't necessarily get a super great strain to failure all the time. A material that has high hardness probably also has high yield stress throughout the material and is very tough. If you watch a lot of bladesmith type shows, you'll see that one of the holy grails of the blade designer is to come up with a blade material that is super hard on the outside but super ductile on the inside, so that when you swing your sword and you smash into somebody else's sword, you either have the outside strong enough to cut through it, or the inside ductile enough that you can shatter their sword and snap their sword because theirs can't handle the impact. At the very least, you don't want yours to break, but you also don't want it to go dull. So you want a combination of materials on there, and that is some real heat treating magic. Fatigue resistance is also a material property that we know a lot more about now than we knew about 100 years ago. And one of the reasons we know more about fatigue resistance is because we've had some tragedies that have happened as a result of not properly understanding fatigue resistance. And so fatigue is how well the material can handle being bent or stretched and then relaxed and stretched and relaxed and stretched and relaxed. And you've probably done this with a lot of materials. You know, if you've got a piece of wire and you're trying to break it, you just get it and you keep bending it back and forth, bending it back and forth, bending it back and forth, and then eventually it snaps. Sometimes it takes a long time. Sometimes, if you do really tight bends, it doesn't take so long at all. That's your fatigue resistance happening there. How many times can this thing take being stressed? Well, an example of why this really matters is the de Havilland Comet. And the de Havilland Comet was one of the first commercial airliners. Now, we don't really think about the fuselage of the airplane as being a particularly stressed body, except for the fact that when you go up to 40,000 feet in elevation, the air pressure drops off a lot. As I mentioned earlier, down at the surface of the Earth, we have quite a bit of air pressure working on us. Up at 40,000 feet, damn it, used imperial again. You don't have as much. At 40,000 meters, you've got even less. So as you keep going up, the air pressure drops. Well, our jetliners, our pressurized jetliners, try to keep enough air pressure inside the cabin, first of all, so that we live, but second of all, so that our ears aren't too uncomfortable as we ascend and descend. That means that the body of the airplane is basically a balloon, and it's been pressurized and it's under pressure from the inside. And that's good. The airplanes are designed for that. And the de Havilland Comet had no problem withstanding that pressure. The first time it flew, or the second, or the third. But as a commercial airliner, these things are taking off and landing a couple of times a day. And after a few years, the early de Havilland Comets, which were the very first commercial jetliners, started to disappear. They'd be flying from one site to another, and they wouldn't get there. Now, this was before there was as many emergency tracking beacons on board, and it's definitely before GPS. So if they were flying over jungle or the ocean, now, it was really hard to know where they were going, and they lost a few de Havilland Comets. And people finally said, right, we've got to solve this. They found a crashed site, and they went through and they started really what is part of modern aviation forensics by taking all the stuff that they could find from that plane and piecing it back together and figuring out how it blew apart. And what happened was that they found a crack that had initiated right by one of the big square windows that they had in their fuselage. Now, you'll notice that modern airplanes tend to have fairly small, rounded corners, okay, on their windows. That comes directly from the lessons learned from the de Havilland Comet. Those squarish corners on the windows And the big windows cause stress concentrations at the corner. So when the plane took off and it went up in the air, it maintained its pressure on the inside, but the outside pressure dropped off, meaning that the fuselage was now containing all the air pressure, just like the skin of a balloon, and it was under pressure. That would cause that one little corner where the stress concentration was to be slightly more stressed than everything else in the material. And that wasn't a problem on the first flight or the second flight or the third flight. But as it happened, every time that it got stretched, it was like folding a piece of material back and forth on itself. And that stress concentration suddenly started to get worse. And then there was a little crack, which really increased the stress concentration, but nobody saw it. And that caused it to get worse again. And that crack got longer and longer. And then eventually the crack started to get far enough away around the airplane so that the airplane would take off. It would get up in the air. Skin would act like a balloon. But now the skin leading from the corner of that window was cracked because of fatigue, and the airplane blew apart in midair, just like popping a balloon. And so there was no warning from the pilot. There was no report of damage. They had to go back and figure this out in post-accident reconstruction. And anyway, the downside is that many people died. The upside is that because the scientists and engineers got on top of that, discovered what was happening, all future airliners had proper stress relief and proper attention paid to the windows and the fuselage to ensure that stress concentrations and fatigue failures would not pop them out of the sky a year or two after they started flying. So anyway, we've taken a look at a number of different mechanical properties of materials. We have a lab coming up where we're going to take thin wires, apply weights to them, apply forces to them, I should say more correctly, and we're going to measure the stress and the strain and do our stress, strain, and strain to failure and yield stress and elastic stress calculations and take a look at all that. So if it's not making 100% right now, we'll come back to it. Some of them, like fatigue resistance, are a little bit difficult to monitor right in the shop. There is equipment to do it, but this is a survey course of a broad range of material science, so we're not going to delve too deeply into any one aspect of the mechanical properties of materials. Rest assured, though, that there are entire degree programs where you can spend 4 years building up for the ability to study this for another 5 years as a PhD student. So if this is exciting, there's more out there for you, but not in this course. Thank you very much. And gosh, I hope I remember to press record at the beginning this time.